Alright, we're going to look at 8.4, which is limits at infinity. So today we'll be looking at limits as x approaches infinity. We're going to look a little bit with graphs, we're going to look a little bit numerically, which we've already seen a little bit, but mostly we're going to look at how to do these analytically, so algebraically there, without a graph or table. But let's start with a graph here. If we're asked to find the limit as x approaches infinity of f of x, that's just going to be over here as our x values get larger and larger and larger and larger. And you can see this graph in particular has a horizontal asymptote here at 1. So that value, as our x values get bigger and bigger, our y value just gets closer and closer to 1. So our answer here would be 1. For example 2, we're approaching negative infinity, and we're still approaching that same horizontal asymptote at 1. So we would also get 1 for example 2. For example 3, they ask us about the limit as x approaches 0 from the left. This is not a limit at infinity, but this is a limit that has an answer of infinity, because you can see 0 would be the y-axis right here. As we approach 0, our y-coordinates just get larger and larger and larger. So we would approach positive infinity. And then the last one here is as we approach 0 from the right. And as we approach 0 from the right, we decrease infinitely. So we would approach negative infinity here. Notice for 1 and 2, my limit as x approaches infinity and negative infinity has the same value. That happens often, but not always. For example, 5 over here, our limit as x approaches infinity approaches this horizontal asymptote here, which is at 8. But as x approaches negative infinity, it appears that we approach the value 2. So they can be different as you approach infinity and negative infinity. Next, let's look at a couple problems here. These problems were more or less going to do with direct substitution, but there'll be a little bit of catch to it. So if I think of like plugging in infinity here, I would have negative infinity to the 5th minus 7 infinity to the 4th minus 7. And so when we're thinking about this, raising something to the 5th is going to make it a lot larger than something to the 4th power, or just the 7 over here. So when we look at this, we really just want to look at our highest variable term, because right here to the 5th power is sort of going to trump everything over here. So if I have negative infinity to the 5th, that is going to give me negative infinity, and that is going to be my answer. I'm really going to kind of ignore this stuff over here that is going to happen, because when we're plugging in huge numbers, whatever's to the 5th power is going to be so much larger than that same number to the 4th power that it's not even really going to matter that much. So we kind of ignore that and only look at that highest exponent. For example 8, we've got x to the 5th minus x to the 3rd plus 1, but x approaches negative infinity. So I'm plugging in negative infinity this time. I'm putting some parentheses around it because I've got to raise negative infinity to these powers. And we know that odd exponents retain that negative, so we're going to have negative infinity to the 5th plus infinity to the 3rd plus 1. And so it's that same thing here. We want to look at our highest exponent. So negative infinity to the 5th is, of course, negative infinity. So that's going to be our answer here. Yes, we do have a positive infinity here, which seems like maybe it should cancel out with that negative infinity. But because it's only to the 3rd power, it's a smaller number and is not going to overtake this infinity to the 5th power. You can always check these with a graph or with Desmos, because if you plug in some numbers here, this is example 7. If we plug in numbers like let's see, 1, 5, 10, 20, 100. You can see that these are becoming more and more and more negative. Here you got 10 to the 10th power, so those are just getting bigger, so that approaches negative infinity. And if we check with example 8 I have here, we can do that same thing. 1, 10, 20. Oh wait, I'm sorry. We should approach negative infinity. So we should do -1, -10, -20, -100, and so on. And you can see these are becoming more and more and more negative. So we approach negative infinity here also. Alright, so let's talk about what's going to happen if we look at the limit as x approaches infinity of 1 over x. So if we think of just making ourselves a table for this, for 1 over x, for 1, we would just get 1. For 2, we would get 1/2. For 3, we would get 1/3. For 4, we would get 1/4. For 10, we would get 1/10. For 20, we would get 1 over 20. For 100, we would get 1 over 100. And so if you look at the values of those fractions, because the denominator keeps getting bigger and bigger and bigger and bigger, we're going to see that that fraction gets smaller and smaller and smaller and smaller, and it just gets closer and closer and closer and closer and closer to 0. So the limit as x approaches infinity of 1 over x would be 0. Let's look at what happens if we have 1,000 in that numerator instead. So I'm going to look at Desmos here, just so I can do this a little more quickly. And so if I call it f of x equals 1,000 over x, and let's add us a table here. So if I plug in 1, still didn't do it. There we go. 1, 2, 3. You can see I'm getting 1,500, 333. But if I start putting in numbers like 10, 50, 1,000, yes, at 1,000 we get 1, 2,000, 5,000, a million. You can see that my fractions get smaller and smaller. Get smaller and smaller and smaller still. So we start with 1,000 in the numerator, but eventually the same thing's going to happen as we approach infinity. So this one's going to equal 0. Also, if we change our function up here to be 1 over x squared, notice we see that we still approach 0. We got 1.25, 0.11, we'll get a 0.01, and then here we have to switch to negative exponents because our values are so small. So this still goes to 0. Here is another example, 50 over x to the 4th. So if we have a number in the top and then x to the 4th, we can see here that our values just get smaller and smaller and smaller and smaller, because even though we have a 50 in the top, these values in the bottom just get larger and larger and larger and larger, which causes us to approach 0. So something we're seeing here for all of these, we had numbers as our numerators, just constant numbers, and then we had some sort of variable in the denominator. So the conclusion that we need to gain from this here is that if we have a number divided by an x to some power, then our limit as x approaches infinity, or actually negative infinity, is going to equal 0. Here, n has to be a constant. It has to be some sort of number. And r has to be positive. R has to be positive because if it is not, you end up with negative exponent situation where you need to move that x back to the numerator. So we're going to see how we can use this information to help us with a problem that's more complicated like this, because I'm going to give you some of these and they are not going to be calculator active, so you're not going to be able to type them into Desmos or to your calculator to see what happens on the table. So whenever we are looking at a problem like this, first of all, we only do this for x approaches infinity. If it's x approaches a number, we're going to plug that number in and try direct substitution. If direct substitution doesn't work, if we get 0 over 0, then we probably might need to factor and cancel or something like that. But if x is approaching infinity, we are going to... Alright, so first of all, we must have x approaches infinity, or it could be negative infinity. So what we're going to do, the first thing, is we're going to divide each term by the highest degree variable from the denominator. So in this particular case, that highest degree variable from the denominator is this x squared right here. So we're going to divide each term by x squared. And so when we do that, we get 5 over x squared minus x squared over x squared is just 1 there. And then here, 3x squared divided by x squared is just going to be 3 because the x squareds can cancel. And then for this last term, one of the x's cancels with one of the x's here, and we've got 9 over x. So, we haven't done a lot with properties of exponents. We would spend a little more time on that if we had it, but properties of limits, I should say. So, the properties of limits tell me that if I am taking the limit of this expression, I can take the limit of each piece by itself. So what I can do is I can do the limit, I'm going to write this, but I usually don't each time. I can do the limit as x approaches infinity of 5 over x squared minus the limit as x approaches infinity of 1 over the limit as x approaches infinity of 3 plus the limit as x approaches infinity of 9 over x. And so usually I don't write that step, but I just want to really explain what's happening here. So if I'm doing the limit as x approaches infinity of 5 over x squared, we just said when we have a number on top and a variable on bottom that is going to approach 0. So we can know right away that this approaches 0. We also know that same thing down here, the limit as x approaches infinity of 9 over x is also going to be 0. So what we end up with here is a limit where we get 0 minus, our limit as x approaches infinity of 1 is just 1 because there's no variable there. It's just a constant term that's going to be the same all the time. We don't have an x there that's getting larger and larger and larger. The value is just 1. Same thing down here for our limit as x approaches infinity of 3. We're just going to get 3 and then plus 0. So what we end up with here is just negative 1 over 3. So we get negative 1/3 for our answer here. Alright, let's do a few more of these. So if I'm going to do example 10, I'm looking at my denominator and I'm looking for my highest degree variable, which is this x squared right here. It's actually our only variable. So just like the last problem, I want to divide everything by x squared. And so what that will do is it will give us the limit as x approaches infinity of 5 over x squared plus, one of the x's will cancel here. We'll have 1 over x over 8 over x squared minus 1. Okay? And so remember, anything with an x in the denominator, as x approaches infinity, is going to go to 0. So this is going to be 0, this will be 0, and this will be 0. So what we end up with here is 0 plus 0 over 0 minus 1, which will give us 0 over negative 1, and 0 divided by any number is 0. So we get a limit of 0 for number 10. Alright, let's look at example 11, example 11. Now, again, we want to divide by the highest exponent from the denominator. So our highest exponent is x to the third here, but it's in the numerator. So we want to divide by the highest exponent from the denominator. So if we divide everything by this x squared here, we will end up with the limit as x approaches infinity of x minus, here one of the x's will cancel, and I will get 4 over x over, the x squareds cancel here, and I just get an 8, and then 2 over x squared. Now, this one's a little bit different because we have this x right here, and nothing's in the denominator here, so we're going to have to deal with that. But before we do that, we already know these pieces with x's in the denominator, they are going to be 0. Because as the numbers get larger and larger and larger, you'll have 4 over 10, 4 over 100, 4 over 1,000, 4 over 1,000,000. It's going to get closer and closer and closer to 0. So what's going to happen here, because I have this x, as the numbers get larger, I will get infinity there because those numbers are going to get larger and larger and larger. But for this, I'll get a 0, so I got infinity minus 0 over 8 plus 0. So that's given me infinity over 8. And infinity over 8 is still just infinity. So that is going to be our answer for this problem. Alright, here's our next one. We've got the limit as x approaches infinity of 4x minus 3 over 2x plus 1. This time, our highest exponent in the denominator is just a single x. So I'm dividing every term by that x. And so I will end up with the limit as x approaches infinity of 4 minus 3 over x over 2 plus 1 over x. And so, again, anything with a x in the denominator is just going to go to 0 as x approaches infinity. So what we end up with here is 4 minus 0 over 2 minus 0. So just 4 divided by 2 is all we have, which gives us 2 for our limit. Okay? Let's do a few more of these. So, for example 13, this time we're approaching negative infinity. But as we approach negative infinity, the same thing is going to happen in dealing with that positive or negative. If we switch back over to Desmos really quickly, if I have f of x equals 1 over x, and I approach negative infinity instead of positive infinity for, negative 1, negative 2, negative 3, negative 4, negative 5. We can see the same pattern is happening, except for our values are negative. But as I plug in numbers like negative 10, negative 100, 500, negative 1,000, negative 1,000,000. My decimals are really small, so it's approaching 0 there as well. So it really does not matter for these whether you approach positive or negative infinity as far as the method that you're going to use. Because even if we go back right here, whenever we're looking at that number divided by x to some power, if x approaches positive or negative infinity, it still equals 0. So same method we're going to use here. So we're going to look at that denominator. We can see that x squared there is my highest variable. So I'm going to divide everything by x squared. And so whenever I do that, I'm going to get the limit as x approaches negative infinity of 8 over x squared plus 2 over x, one of those x's will cancel, minus 1 over 9 over x squared plus 1. And anything with an x in the bottom is going to become 0. Everything else stays as it is, so we got 0 plus 0 minus 1. On the bottom, 0 plus 1. That's just going to give us negative 1 over 1, which is negative 1 for our answer. Okay. For example 14, our highest exponent in the denominator is a 2 here. And actually, I'm going to change this so this is a negative infinity. So fix that there. And so we're going to divide by x squared here, and we are going to get the limit as x approaches negative infinity of, here we're going to get 4x minus 10x to the third over 15 over x squared plus 1. And so this time we've got that negative infinity to plug in. So I've got 4 times negative infinity minus 10 times negative infinity to the third over, this will be 0 plus 1 because you have an x in the denominator here. So we got to do this a little bit like we were doing example 7 and 8. This is going to give me 4 times negative infinity is going to give me negative infinity. And then negative 10 times negative infinity to the third is going to give me positive infinity to the third power over 1. And because that infinity is to the third power there and it's positive, it's going to be larger than this negative infinity here. And so I will just end up with positive infinity there for our answer. Okay, and our last one that we have here, before we look at sort of some generalizations, is we've got 9x squared minus 3x over 8x plus 7x to the fifth plus 2. So our highest exponent from the denominator here is x to the fifth. So we have to divide everything by x to the fifth. And that will look like this. The limit as x approaches negative infinity of 9 over x to the third minus 3 over x to the fourth over 8 over x to the fourth plus 7 plus 2 over x to the fifth. And anything with an x in the denominator, as x approaches that negative infinity, that value is going to approach 0. And so we will end up with 0 minus 0 over 0 plus 7 plus 0. And so we get 0 over 7, which of course is just 0. So this is a strategy that can be used every time. If it makes sense to you, just stick with it. But there is a shortcut that we can use to help us with this, because there are some patterns that we can see each time. So if I go back to that first problem that we did here algebraically, if I see that I've got here an x squared on top and an x squared on bottom, notice here, let me highlight that, I have an x squared and an x squared on bottom, and so my highest exponent on top was the same as my highest exponent on the bottom, and notice that my answer was negative 1 over 3. For 10, I had my highest exponent on the bottom. I got an answer of 0. For 11, I had my highest exponent on the top, and I got infinity. For 12, my highest exponents were really just to the first power, and they were the same on top and bottom, and I got 4 divided by 2, which was 2. For 13, I had the same exponents on top and bottom again. Notice that I got negative 1 divided by 1, which was negative 1. And here, highest exponent was on top, and I got infinity. Here, my highest exponent was on the bottom, and I got 0 for that. So, there is a very strange saying that we sometimes use, or I use often anyway. I didn't make this up, somebody taught it to me, so somebody else uses it too, called but no. Eats DC. So this is a strange saying right here, but here's what it stands for. Bobo is bigger on bottom, and that O right there is a 0. Okay, so what that's telling us is that if our exponents are bigger on the bottom of our fraction, our limit as x approaches infinity is going to be 0. Notice that happened. Right here, I had the x squared on bottom, only the x to the first on top, I got 0. Right here, I had x squared on top, x to the fifth on the bottom, I got 0. So as soon as you see these problems, if you see that you have a bigger exponent on the bottom, you will know that the answer is going to be 0. The next one is bigger on top, not 1. And so what this means is it does not exist, or infinity. So we got infinity for all those where we had a bigger exponent on the top. Now, one reason I did go through teaching you all of this is that you can't really tell whether it's positive infinity or negative infinity unless you do this longer version that I have been teaching you here. So in order to be able to tell whether does not exist is positive or negative infinity, you do actually have to go through these steps. And the last thing that we have here, and our last expression here is eats DC. This stands for exponents are the same, divide coefficients. So whenever our exponents are the same, like we have here, we can just take the coefficient in front of our highest exponent in top and bottom, like here is a -1, here it is a 3. We can divide them, we get -1/3. So if you use Bobo-Botno, you can get the answer to a lot of these questions really quickly. So let's look at a couple of examples using that shortcut. So if we're looking at the shortcut here, for these rational expressions here, if we're asked to find the limit as x approaches infinity or negative infinity, for which the problems we look at, it's not going to make a difference. There are some where it doesn't make a difference, or it does make a difference, but we're not going to look at those. We'll save those for calculus. So if I'm trying to find the limit as x approaches infinity of 4x over 20x plus 1, they have our highest exponent in the top is this x, highest exponent in the bottom is the x. So we're just going to divide those coefficients. This is exponents are the same, divide coefficients, each DC part. So we would just get 4 over 20, or of course that would reduce to 2/10. I guess I should have gone straight to 1/5 there. For 26 here, I've got an x squared and an x squared here, so I know those are my highest exponents, top and bottom. They're the same, so I just divide my coefficients. That's going to be a 3 divided by the understood 1 that's here, so I end up with just 3 for that answer. Whenever I look at 27, again, exponents are the same here, so 6 divided by 3, I could tell this is 2 right away. For 28, x squared and x squared, exponents are the same, divide your coefficients, each DC. 4 divided by 8, of course, will reduce to 1/2. So these should be really quick whenever you're doing this. For 29, you can see the highest exponent in the top is a x to the 3rd. In the bottom, it's x to the 4th. So my exponents on the bottom are bigger here. So this is Bobo, bigger on bottom, 0. So I will get 0 for number 29. For number 30, again, I got x to the 4th on top, x to the 5th on bottom. So this one's bigger on bottom, so I would get 0 for that one also. For 31, only an x on top, I've got x to the 4th on bottom, so I will get another 0 for that one. For 32, I've got x to the 8th on top and bottom, and those are my highest exponents. So I would divide coefficients for this one. This is a each DC. 12 divided by 3 would give me 4. For number 33, my highest exponent is on the top, which is our Botno, bigger on top, not 1. So I would know this is D and E, but I would need to go through here and tell whether or not this would be positive or negative infinity by doing the problems like we were doing in the beginning. Same thing for 34. This is bigger on top, so I could put D and E, but to know whether it's positive or negative infinity, I would have to look at what I was plugging in here for the problem, so you would need to look at those. So that's sort of an overview of how you can do this pretty quickly. You're going to have a worksheet to do with this. It should not take you too awful long. If you finish the worksheet, then you may go ahead and start on the test review.